Now they have other names, sometimes flip back and forth. It'd be nice if you can keep track of all of them. This is also called a scalar product. And this is called a vector product. Anyone want to take a wild guess why this is called a scalar product?
Because the number you get after you multiply a scalar.
Yep. And this one?
It's the same thing but a vector.
For the purists in the group, it actually produces an axial vector or a pseudo vector. But the pseudo vectors and vectors smell and taste the same. So, and one last, and I do this just for some sense of completeness. This is not the language that I typically use, but this also is called an inner product. And someone take a shot here? Yep. Okay, right now we're concentrating on the dot product or the scalar product. So when you're multiplying vectors, remember I can break any vector up into parts. Now we generally start with the parts and we then create something out of it. So for example, if I gave you a vector to the right of a magnitude of 3 newtons and plus a vector going up of 4 newtons, what is the magnitude of the total force? This is a flashback to Pythagorean theorem.
Yeah.
Yes, it would be 5. It's a 3, 4, 5 triangle. So the magnitude, the resultant right here is a 5 Newton force, and that angle beyond the scope of the course is knowing how to get this, but it's a 53-degree angle. Now, so any vector I can break up into 2 perpendicular parts. So if I have a vector A here and a vector B, and I multiply them, well, A I can break into 2 different parts. So I've got part of A that's in the direction of B and part of it that's perpendicular to B. When I multiply the parallel parts, I'm doing a dot product. When I multiply the perpendicular parts, it's a cross product. So this would be the A, what I'll label as A parallel, and then A perpendicular. And so A dot B is just the magnitude of A. Sorry, try that again. It is the magnitude of the parallel part times the magnitude of B. Now, if it's in rectangular form, it's really simple. Let me show you what I mean by that. If I've got 3i hat plus 4j hat, and if you want to say I hat is to the right and j hat is up. This is rectangular form. It's a vector I've written in 2 parts. If I threw newtons after it, it would be this vector right here. Dot product, 4i hat minus 3, stuck the same numbers. We can do different numbers. 5i hat minus 2j hat. What I do is I multiply the parts that are parallel to each other. Well, I hat and j hat are not parallel to each other. They're perpendicular. So I multiply the parts that are parallel. 3i hat times 5i hat is, and I appreciate no one said I hat after it because it is a scalar product. And then multiply the j hat parts together. Yep. Minus 8. And so the dot product here is 7. There's no direction to it. It is a scalar. It's just a number. So, questions up to here before I connect it back to that? Yes?
But why do you put minus?
Why minus 8? Technically, it's 4 times negative 2. So technically, it's plus negative 8, which is the same as subtracting 8.
Can you
Alright.
explain the middle triangle with the A perpendicular parallel?
This, I have two vectors here, A and B, and if I want to do a dot product, I have to figure out how much of one vector is in the direction of another. So part of A is in the direction of B and part of it's perpendicular to it. And so what I'm doing is just establishing that my dot product is this length times that length. That was not a convincing okay there.
Yeah. Maybe if you
It-
build a box.
What were you
You're
suggesting?
you're connecting the two vectors.
I'm multiplying whatever that length is times that length. Did Johanny?
And then the equation for I had and J had, that's to find the rectangular, you said? To find.
This is rectangular form right here. That. So when multiplying vectors, doing a dot product between vectors in rectangular form, you just multiply the I hats together, you multiply the J hats together, add. All right, let's see if we can actually put it in context and maybe that'll clear up some things for you. So if I've got ground and I have a box on the ground, and the box is gonna get moved, it's gonna move from here to here. So the box moves, and we'll say that's 3 meters. Now, if there are no forces acting on it, it's just moving by itself, no work is being done, it's just cruising along. Except if I apply a force, if I'm applying a force here of 4 newtons, well, that force is completely in the same direction as the displacement. If I do force times displacement then, it's 4 newtons times 3 meters. Well, what? Yes, Newton meters. Now, if that's too much, you're thinking, Newton meters, so many words. Is there a single word we could use? You're in luck, there it is. In this context, Newton meters doesn't always work out this way. That's not the context. If in this context, when you do the dot product and you get newtons times meters, this is a joule, symbolized by a capital J. And someone want to take a wild guess what scientist was being honored by this? Yep, that's the one. So this force times displacement would be 12 joules, or Newton meters if you want to stick with that. Now, of course, we got to come up with another word, because you can't have, there's no such thing as too many vocab words, right? And if you want to take a foreign language, there's that. Force times displacement is a special name in physics. It is called work. And one of the reasons why I don't use capital W for weight. All right, let's change the problem slightly. Instead of having 4 newtons pushing that way, I have 4 newtons pushing this way. What is the work now?
It depends on which way you're saying is positive or negative.
It actually doesn't.
Then
Negative
what-
is what?
Dave, that's the final answer?
No, you're not saying.
Oh, you want to make it to the right positive? Is that what you- I heard you say -4.
Yeah, so it would be -4 if it's pushing this way.
Okay, so you made that way positive, so if it's to the right is positive, I'd have -4 times 3. Now suppose instead we made the other way positive. It's now 4 times -3, which is still the same, so that's why it doesn't matter. So we have -12 joules of work being done. The object's still moving to the right. It'd be like something's coming towards you and you push it on it, you're trying to stop it, but you're being pushed backwards as it moves. If instead, questions before I throw in another scenario? Before Newton is pushing straight down as this thing moves to the right. What is the work now? The work being done by the 4 Newton force. Remember that when you do a dot product, you're multiplying parallel parts. So how much of that 4 Newton force is parallel to the 3 meter displacement? Why don't you go ahead and say it?
0.
Yeah. There is no work being done. If the force is perpendicular to the motion, the work is 0. So a guy can have no work being done for three different reasons. I can have no work done if there's no force applied. For instance, I'm not doing any work on the notebook right now. I can have no work done if there's no displacement. I'm pushing on it, but it's not moving. So no work is being done. Or if I apply a force perpendicular to the motion, so pretend that this hand is separate from this hand. So right now my finger is doing no work to it because the finger is perpendicular to the motion. This finger. If again, this thing is still displacing to the right. If the force is like that, am I doing negative work or positive work?
I don't think so.
It would be, because the part of the force that is parallel to this is going to the left, part down, part to the left. This would be negative work. If the force were like that, that force would be doing positive work, because part of it is in the direction of motion. All of this will come back. Yes, John?
You said if the force is perpendicular to the motion, the work is 0?
Yes. I know what you're thinking. You're thinking, you promised us a derivation. Where is it? Okay. I'm gonna meet that need. Any questions before I do the derivation? And cross products we'll get to in chapter 8. According to Newton's second law, what is force equal? Yes. So the force, if this is the total force, so if this is the total force acting on A, then this is equal to the mass of A times the acceleration of A times the displacement. So now I've got this acceleration times displacement with a dot product. What does that equal? Well, let's work it out. Acceleration, what's the formula for acceleration?
Change in velocity over change in time.
So change in velocity over the change in time. So that's just V final minus V initial divided by time. displacement, let's actually do, average velocity.
Initial plus
Initial divided by 2.
There's two formulas, so we need them both. So one of them is,
initial plus final divided by 2.
and what's the other formula? This is true if acceleration is constant, which we're assuming right now. And the other one is always true. Checking it, if you already are. Tension is melting. I'm gonna nitpick the language.
Oh, no, it's a displacement over change.
Yeah, displacement over time, change in position over change in time. So delta x over delta t. Hey, I got a delta x over there. I'll just put it over t. So what I'm gonna do is I'm gonna take this and plug that in for acceleration. I'm gonna solve for my delta x right here, plug that in over there, and then it'll just unfold naturally. So from based on this, my displacement therefore is just 1/2 times vi plus vf times time. That's, I multiply both sides by time, our time comes up here, and divided by 2, so then it's multiplying by 1/2. So what I have over here is I got mass of A times, I have only one object at this point, so I got mass times A, which is Vf minus Vi over T. Dot product with 1/2 Vi plus Vf times T. Now, the things that aren't vectors when I'm doing a dot product, I can just pull them out and just multiply them normally. I've got a t here and a 1/t here. Those t's would cancel out, so time goes away. The 1/2 I'm just gonna bring up front, so I got 1/2 mass times V final minus V initial, dot product, V initial plus V final. So now I've got this dot product, I got two binomials there, just to bring back some good old math vocabulary. How do you multiply binomials? Guessing there's at least one person in here who remembers. I suspect half of you remember, but are afraid to say.
The first numbers of the parentheses? Like, so VF times VI, or, geez, it's gonna be.
So so you multiply the first one, then?
Yeah, and then the first one, then the last one, and then the two on the inside, and the two last ones.
Yes, otherwise known as FOIL.
Yeah, I barely remember that.
I'm assuming FOIL is still being used as a common term for this. So I'm gonna multiply the first terms together, then the outer ones, then the inner ones, and then the last ones. All right, I'm gonna keep the dot product in there. So I got 1/2 mass times, I got VF dot VI, that's multiplying the first ones. Then the last ones plus VF dot VF. Then the inner ones minus VI dot VI. And then the last ones minus VI, lost my vector symbol there, dot VF. All right. It's a lot of letters. little bit of alphabet soup going on there. Let's see if we can simplify it down into something more manageable. If I say the commutative property of multiplication holds, what does that mean? What does it mean to commute? If you commute to work.
Travel.
Travel. So commutative property means basically you got two things you're multiplying together. It doesn't matter the order. You can move one from the first term to the second term, no problem, or first factor or second factor, it doesn't matter. What I'm getting towards here is that I have vf.vi minus vi.vf, they go away. Because the order doesn't matter when you multiply it in a dot product. So I'm left with just, I got rid of half of right there. Now I'm doing a dot product with a vector with itself. Now remember, when we do dot products, we care about how much is parallel to the other one. How much of VF is parallel to itself? Perhaps too abstract, so let's do it differently then. If I do 3i dot 3i, I hat, what does that equal?
9, I have.
Pardon?
9, I have. No, I have.
No, I hat. It's a scalar product, it's 9. Let's flash back to what we did over here, where we just multiplied the like components. So the same thing holds true here. So if I take any vector dot product with itself, it's just the magnitude squared. So this VF dot VF is just the speed squared. I still got that 1/2 m up front. Minus VI squared. The vector symbols have gone away. My final answer is a scalar. But wait, I'm not done. We are getting close to the important part here. Any questions up to here?
Why did the vector symbol go away?
Because when you multiply, first off, it's a dot product is a scalar product. So in this example here, when you multiply, you just multiply